Okay, so basically the activity that I gave you was something that I, when as an undergrad, learned was quite eye-opening for me, which means that every chemical, and partly because of the fact that when we read about certain environmental chemicals, we found out that a lot of these chemicals actually eventually turn out to be very, very dangerous for not only human health, but also a lot of other life on the planet. And also, okay. So no one wants to talk, or are you just shy people by birth? No raise hands. I miss Zoom. All right, so like I was saying, every chemical has to have a material safety data sheet, which should enlist all the hazards, whether on the human health or on the ecosystem that the chemical might have, and then a lot of other details on where the source is, how it should be discarded. If you come across the chemical specifically in the lab, then how should you handle it? Because a lot of people do not know that water is not the solution to every chemical. Sometimes some chemicals dissolve in water, and it's going to be even more dangerous for you to wash it. So a lot of that information, when it was given to me as a student, it was eye-opening for me that we hardly ever think about how many chemicals there are around us and what impact do they have on the planet. And then I think, again, the second most important thing that I learned was we use shampoos all our life. And around the time when I was doing my undergrad, they were phasing out SDS with different other chemicals, just because SDS or SNS were found to be carcinogenic in nature. Okay, so all of that information I thought is something that every individual should know, just like we ask you to know about your environment, just like we ask you to know about the implications of what you do on the environment. I think information is also key because most of these chemicals, because we don't know how they're going to interact with the human body or with animals. And then a lot of ethical questions on testing drugs on mice and all that discussion arises because it's close to a human body, but is it actually going to really mimic the human body? So there's a lot of progress there as well, but I think a lot of this wasn't found to be true. And when they caused cancers, or for example, when these pesticides caused for deformed eggs of different birds, that's when people realized that, oh, we should not have used pesticides because look at what we're doing with all the biodiversity that was around us.
Like DDT.
Exactly. Yeah. So I don't know, is there no one, like you guys work hard, but you want to talk about it? Thank you, Alison. Go ahead.
So I would like to talk about sodium fluoride. Sodium fluoride is a common chemical that is used in toothpaste. It is hazardous for the human health, specifically for the kidneys and the skin and all the the primary organs. However, it has its environmental effects as well. It's stable, like chemically, it's sodium fluoride fluoride is a very stable compound, but when it reacts with water or with soil, it emits the toxic gas fluorine. So again, in the water environment, water bodies, sodium fluoride up to an amount of like 46 milligram per liter is an endpoint according to European industries. Even if it's more than that, it can cause acute illnesses or acute problems to fish and other vertebrates.
Right. And this information was new for you?
Yes.
Okay. Anybody else before we move to the yes?
I was particularly confused about my ingredient, which I use for
Yeah.
sodium borate sulfate.
Okay.
It's in my face wash, but the MSD has mentioned that it is actually an irritant for the skin.
Yeah.
So it irritates the skin. So how it is being used in the face wash?
Yeah. So basically, in certain quantities, and as you know, a lot of beauty products would ask you to test it on your skin first because it's not most widely tested. And if you look at the intersection side of it, they say, oh, it's mostly tested on global South white men and not necessarily on brown men and brown women and other people of color. And so it's not really widely tested. So as just like for example with COVID, your particular experiment sample wasn't, if it wasn't a representative of the entire population, then complications would have happened. So a lot of these chemicals have the capacity to cause irritation to skin, not for everyone, but for many. And so they have to put it there, just like they put it for several chemicals like hair color that you should do a skin test before you apply that to your hair. Because these chemicals might cause something. And I think in excess, they definitely do cause it. But then this chemical doesn't come on its own. It comes in combination with the EPA, so they have the ability to combine it and remove what's found. And yeah, so essentially that was the purpose of this. But a lot of these chemicals do have side effects, do have smaller implications on the skin that you tend to ignore. But they've been created in combinations where they combine or react and then take that dirt away, or let's say take that dead skin away. But oftentimes they can cause toxic problems. And mostly like in 15, 20 years time, we'll find out that it is actually carcinogenic. But you have to wait that long to find out that it is carcinogenic. Also the medicine particularly is, which is why I highly avoid taking any medicines at all. Because they test the drugs, but they haven't tested it for a long time. And suddenly they find out that a particular component was not really good for a particular organ in the body. Anyway, so that was, like I said, when I was a student and I found out about this, it was really, really fascinating for me. And I thought that you might find it equally fascinating as well. So, and yeah, and before I move on, I have to tell you guys what I told some of you earlier as well. In the quiz, there were some very, very basic questions. The quiz was essentially for me to see how much are you listening to me in the class, but also all the other instructions. So for example, tragedy of the commons was something that I didn't really teach, but I asked you to read chapter 1. And I realized that a lot of you do not be reading anyway. So for me, it was like a test of how much are you listening to me in the class, and also how much are you listening to the instructions. So that while there might be a lot of people who are listening to the instructions and are fully present in the class, it just gave me a sense that I probably do need to come back to some basic content and some of the basic concepts and revise it again and again, so that at least you go away with those when you leave the class. Because in the end, the purpose of this class is to teach you the basic science. I never promised to make you the Einsteins. I just promised to teach you enough to navigate in the world of science relating to the environment. So that's why I will be talking about some of the quality parameters. And another reason for doing the exercise was for you to think that whatever chemicals we eventually see, like later in the course, we'll look at the standards that have been set for certain chemicals in Pakistan. But there are so many more chemicals around you which you have demonstrated in the pilot activity, that even one particular medicine that you use has that kinds of chemicals that is going to get into your environment, in your data. So where are the quality parameters for those? So shouldn't all of these be monitored in our water or in our hydrosphere or lithosphere as well, because we are discarding it as a residue to the environment. So we'll try not to, I'll try not to talk at you too much, but kind of listen to what you have learned in this time. So we did talk about certain pollutants. And so I'll ask you to think of all the spheres and think of some of the pollutants that you think should be monitored to monitor the health of the environment. So while you think about those, I'll take question from one or comment.
कमेंट किया कि आपने बोला कि मेडिसिन वगैरह में बहुत से केमिकल्स लाइक होते हैं, लेकिन मेडिसिन में टेस्टिंग ऐसे होती है कि कोई भी मतलब जो हमारे पास मेडिसिन होती है ना, उसमें हमारी बॉडी में जो पर्टिकुलर डिजीज है ना, उसके लिए वो इफेक्टिव होती है, लेकिन बाकी हर मेडिसिन के साइड इफेक्ट्स जरूर होते हैं। आई मीन टेक से वो टेस्टेड होती है, लेकिन सिर्फ उस चीज के लिए जिसके लिए उसको बनाया गया, उसके हर मेडिसिन के साइड इफेक्ट्स होते हैं।
Absolutely, and that's exactly what I want you guys to think. Like generally, जब chemists कुछ बनाते हैं या biology वाले कुछ सोचते हैं, तो वो ये नहीं सोचते, जैसे मैं आपको कह रही थी, when you look at the cycles, you're always taught those cycles in silos. आपको कभी भी उन सबको merge करके नहीं सिखाया जाता that the air you breathe also has sulfur, also has nitrogen, also has carbon, also has oxygen, also has all the other molecules that there are and any other pollutants that are added. और वो आपकी body से क्या करते हैं? That we do not know. Particularly the combinations that we've created now. How quickly the environment is changing, we do not know. While the drug is designed to go and target a certain organ or a certain space in the body, or like I said, there's been a lot of progress on this to precisely put the drug where it's meant to be. But the body is designed such that generally you're taking a medicine, it's supposed to flow, with blood or with other fluids and go to every part of the body. Ideally, it should just go where it's meant to go, but does it actually go where it's meant to go? So technically, your entire body is drawn to a certain chemical. And it's not always precise drug targeting. I think that there's a lot that we need to get back to. Yes, there's been a lot of progress. And yes, there are side effects, but how many people get to know about the side effects? And how many people know that the particular injection they're taking or particular drug they're taking actually has not just one ingredient, it's not just Panadol, it's actually like 10 things that are shown in that. So I think the authorities owe that information to the individual, and the individuals need to open their eyes to see what's in it. Hospital environment, which is that I was told by the waste management company that a pharmaceutical company dumped all of its expired medicine into whose edible. Now that's new, right? That's something that we do not know. Those drugs are new for us. So anyone who's using water downstream is going to be impacted by those expired drugs that none of our population or the population of our ancestors has been impacted by. So it's, I'm not saying that I'm right or wrong about what I say. All I want you to think is that it's complicated, that it's not as simple as you're taught in science. For example, they tell you, ये chemical, ये nanoparticle, gold का जाके heavy metal को remove करेगा. जब वो environment में जाएगा तो सिर्फ वो heavy metal नहीं होगा. Lab में उन्होंने उसको heavy metal के against test किया होगा, उस particular pollutant के against test किया होगा. Environment में जाएगा तो हजार और चीजें होंगी, हजार और चीजें आप लोगों ने देखी हैं अपनी पैकेट. So how do you know that that particular nanoparticle is only going to remove that particular pollutant? I think it's way more complicated. Problems are way more complicated than we present in the solutions. So I think that was the purpose of bringing this to you. So I hope that makes sense. And I can take questions from Asad, and then I can take some comments on what you think some of the quality parameters are that should be monitored to look at the health of the environment. Yes?
Actually, to just on the medicine, like कैसे side effects which what people want. So this situation में is that the fault of the company or the individual? आपकी जो कंपनीज होती है जो भी कोई फॉर एग्जांपल तो उसकी साइड इफेक्ट्स are like very easily available to the public. If the individual doesn't decide to like research and just get it moving that doesn't have any doctor system very easy job
I don't know where I'm taking this conversation. So you know that I'm a very, so I respect the medicine, like that area of science that's doing a lot of research. So for example, I have a lot of respect for people who created the COVID vaccine. So I'm not trying to discredit any of the incredible research and science that has happened in discovering drugs that has solved a lot of human health issues and maybe issues of other spheres in the environment as well. But it's not as simple as here's the problem and here's the solution. There's so many layers. Like how many medicines tell you that there's such a huge implication with the environment? I think very few. And then in countries like ours where wastewater can flow by your home openly, and you don't even know what that means. Right? You don't know that wastewater now has a lot of population that is taking different kinds of drugs, is using different kinds of face washes, and all of that is just flowing by you. You don't even know how that could enter your groundwater or the water that you're drinking. So I wanted to get you to think about the complication without discrediting the science, without discrediting the research and all the important work that's happening. If that makes sense. So yeah, quickly, indicators for environment.
And we could measure the microplastic pollution, which has become a major problem for oceans because if fish ingest it, it can also result in biomagnification.
Exactly. And the plastics one. Yes. Yeah. Absolutely. So all the SOXs, NOXs, GHGs that we studied, they are essentially indicators of the health of the environment, right? How do we say that the earth is warming? Because we look at the concentrations of CO2 and we say, oh, it's gone way past 350 ppm to wherever it has gone right now. So that's an indication, and that's why we were looking at it. And biosphere, okay, we talked about this a little bit. Maybe I can leave this bit and now come to it. Why I wanted you to think about this. So when I talk about temperature, and I tell you that the temperature of a certain sphere, and in this particular case, hydrosphere is changing. What do you think would be the implication of this one parameter, which is temperature, on the health of a water body? Just think, like you don't have to talk. And then now if someone wants to talk, they're welcome to talk. Yes.
If the protein is distributed inside the ocean or water.
Exactly. So that thing isn't mentioned here. So I've just mentioned a few parameters, and I really love this thing, by the way. Behram, I'll come to you. But what I haven't mentioned here is, you know, fish and a lot of life below water, they give each other signals. And those signals are dependent on the flow of salt, the temperature, the currents, the chemical signal that's coming from a predator to a prey. And changes in these would cause changes in that particular convection or movement, and it would eventually make a certain fish more prone. So for example, if you remember, noise pollution was one of the reasons why dolphin population, freshwater dolphin population in China got extincted, right? It was because there was so much noise that they could no longer communicate with each other it's like their locomotion was compromised when we looked at the biosphere. So it's not just one component, it's like several parameters. Of course, the quality of water was degraded, Of course, the flows were degraded. I'm sure they needed a certain amount of oxygen. But then all of those parameters are really related to each other as well. And here I only refer to the chemical parameters. So you might think temperature is just one parameter which would increase or decrease. And temperature does what temperature does to us. When it's too hot outside, it's difficult to breathe. At least we have the capability to maintain body temperature. There are many species for which it's super difficult to maintain their body temperature. Even a slight change in the temperature of the environment could wipe out their entire population. But it's related to so many other things. So if you remember carbon dioxide, and we'll get to how temperature is linked with the concentration of carbon dioxide, how that is linked with the acidity or basicity of a water body, how that impacts life below water. And again, how temperature is related to pH, how temperature is related to toxicity of compounds, how temperature is related to, we talked about salinity in lithosphere, not really talked about it. So for this lecture, I don't think there's a lot of reading that I wanted to do. I have the definition for all of these in the annex slides, which I hope you can read and try and understand, because the objective of this is for you to understand these complicated interrelations, which are not as simple as if the temperature increases, this would happen, and if the temperature decreases, that would happen. It's how one parameter impacts on the other. And then one parameter that's often used and that probably might be really easy for you to think about is conductivity, right? And we read in our childhood that generally water is a poor conductor of electricity. But once you add salts, electrolytes into it, it becomes a good conductor of electricity. But that increase in conductivity also indicates presence of excess pollutants. Not always. So for example, of course, seawater has more salt, so its conductivity higher than fresh water. So it does not indicate more pollution, it just indicates the natural state. But oftentimes, excess conductivity or increased conductivity is increase in pollution. And that could be natural as well. I'm not saying that it's almost always human beings. So the water that erodes, it takes a lot of chemicals. The water, for example, that washes the fertilizers and bring nitrates and phosphates to the lakes, that's all increase in conductivity, which eventually causes eutrophication. And then, with salinity, I would also like to relate it with density and total dissolved solids. So when you look at the waters, for example, the water that's rushing out of a glacier, you'll see a lot of suspended soil particles in it, or sediments, as we call it in our language. And a lot of them would settle with gravity. We call those that are visible these suspended solids. But then there are other solids which are not visible to you. Those are called dissolved. And generally you have to evaporate the water to get that salt. And that salt is not just sodium chloride, it could be salts. For example, it could be boron, it could be other things that they're found in the environment as well. And then again, they're all related to each other. How is it related to temperature? If the temperature increases, we know that the chemical activity will increase. So the salinity or the conductivity could increase. And so all of this is eventually related. It might be worth talking about the dissolved oxygen. And it's if the temperature is increased, the dissolved oxygen decreases, because then it's difficult for the life form would need more oxygen and to maintain the temperature, and the exchange between the oxygen in the atmosphere and the water body is difficult. So just looking at how this one parameter impacts every other parameter, and we might look at some of those again in some of the next slides, is important. But Behram had something to add, so I'll Exactly. So it impacts the chemistry of the biology as well. Right? There are a lot of hormones, there's a lot of chemical signaling that happens in the body. But then also think about very basic parameters like osmosis या diffusion. एक cell है और उस cell के around अगर salinity बढ़ गई है, so you know that water tends to flow from place that has lower salt concentration to higher salt concentration ताकि बाद उसकी population बराबर हो जाए. That's how environment is designed. अब अगर cell उस तरह से diffuse करने शुरू हो जाए, अगर cell lower salinity से higher salinity तरफ move करने शुरू हो जाए, तो फिर that cell would burst as well. And it could be both, like it could be the other way around as well, that if the concentration of salt increases in a particular body, then water would come in and cause for the cell to burst. So it could be desiccation, or it could also be like bursting. So yeah, like many layers, many important and incredible information that you need to know. But why do we bother knowing about all of these? Now, I've tried not to complicate, trying to tell you about the complexity without complicating it too much. So there's not a lot of biology and chemistry that I've put in, but it'd be nice for you to think, what does that oxygen level mean for a certain species? So if you are in the north of Pakistan, where the water body is fresh, where the dissolved oxygen is high, you'll have drought. But you can't expect to have drought maybe here. But then generally, like a normal water body has 6 to 8 milligrams of dissolved oxygen, and that's considered healthy. So generally, like in the water body that you see, these like perch and all of those would be some of the species that you find. But if you're, for example, trying to grow that species with these conditions, you're not going to get it. Or if the natural environment of this is changed into this because of addition of extra chemicals, or because of, let's say, change in the concentration of salt. So we talked about salinity. Naturally, seawater has lesser dissolved oxygen than fresh water. So how if we add pollutants to, so let's say if we were to increase the salinity of or the temperature of the seawater, how that would impact our dissolved oxygen and how that would automatically impact the life that lives there. So I hope this makes sense to you guys. Yes. Yeah. So this refers to like which species would be found in abundance at a certain dissolved oxygen, which essentially means that these are their natural environments. And some of them might be able to survive a little lower or higher, but past that they wouldn't survive. So if for any reason, natural or anthropogenic, that is changed, that means that whichever species has the ability to survive and adapt would survive. The rest of them might die. So yeah, that's what I wanted to tell you. Anyways, so just like building on the discussion on salinity, like I said, technically water is neutral. But once you add the salts also, or the electrolytes also technically are neutral. So sodium and chloride, they come with their own charges, but they're all neutral. But then because of the polarity of water, when you add it in, its conductivity increases. And that conductivity is measured. So now we talked about conductivity, and we talked about presence of salts or electrolytes in the water, which increases the salinity. But then that is also related to conductivity. So conductivity could be an indication of salinity, and salinity could be an indication of conductivity, like however you want to look at it. And if you look at the life forms that change naturally, so because we know that naturally seawater is more brackish or more salty or is more saline, there would be more water, or like more life in oceans when there's high salt. So what's actually super unhealthy for freshwater body is the natural environment of marine life. So the species of freshwater will decrease when the salinity increases, but the species in ocean will increase when the salinity increases, because this is their natural environment, and this is the natural environment of a fresh water body, if that makes sense. So if you look up, like if you see the freshwater body species are increasing and then decreasing up to a certain extent, and we can relate it to this with the plants. But then for brackish and marine water, as the salinity increases, you will naturally have a habitat that supports different life forms. And like I said, a lot of these, the salinity, the change in temperature. So water naturally is designed to become homogeneous. So if you add salt, eventually all of it will be dissolved. If you heat it, all the heat will try and, then the solution will try and homogenize. And in that principle of becoming a homogeneous mixture, a lot of convections are created. A lot of natural currents are created across the oceans, and that allows for fishes to move, for salts to move, for the temperature to become balanced. But that also, unfortunately, allows for pollution to move in the environment. So a lot of these natural processes are also the expediting movement of a pollutant in the environment. And back to what I said, like I'm not, when we say salinity is not good, we are referring to the freshwater resources inland and not necessarily to marine life. So just wanted you to think about different ecosystems and their natural or baseline conditions and what that would mean to the life that is found there. And if you look here, it tells you the different species that could survive in certain kind of conditions. So like salt water, all of these species do survive. And then freshwater, these are the species that will survive in freshwater. So if a freshwater body if one of our industries, for example, was dumping, even if it's a salt factory, which otherwise looks harmless, would dump its wastewater into a water body, all of these species wouldn't be able to survive. So just like think about those teeny tiny changes that would happen in the environment. And again, naturally or anthropogenic. So don't be intimidated by this. I think the concept of pH cannot be explained without going into some of the details. Basically, all I wanted to think about is we are talking about carbon dioxide in the atmosphere. I will continue to talk about how carbon dioxide sinks are created like natural sinks are already there in the form of oceans and also in the form of land. So I'll tell you how when we put a lot of trees, that carbon dioxide is fixed and it's also sequestered and captured from the atmosphere for its concentration to be reduced. Okay, and then similarly in the ocean is also like a similar sink, but what it does is the carbon dioxide diffuses into the water. And when it diffuses into the water, it forms a weak acid, which is carbonic acid. And those then, of course, give acidic conditions naturally to that environment. So whichever, and this is all natural. So we're not, we haven't made any of this up. This is naturally how the species evolve. But that adds on to reducing GHG or CO2 in particular in the atmosphere. So it's absorbed. Let's say it's absorbed. Forget the equation. Let's just say that carbon dioxide, which is here, is absorbed into the ocean. Forget what happens afterwards and then what happens to that species afterwards. But between the change from CO2 to carbonic acid to eventually carbonate, which is something that is useful for life, that life will use, the pH also changes. So while this is acidic, this is a basic condition. Now there are two ways to look at it, and it was really tough for me to explain it last time as well. If I could avoid all the chemistry and just think about the environment, if the pH changes, the species that would be available to the environment or would dominate the environment would also change. So at a certain pH, yes, there are. Yeah. Huh. Exactly. So there are like a lot of acids and bases that react with each other and eventually salt and water is formed. And those are again natural cycles. And that could also happen in the body as well. And then, yeah, there's like the buffering mechanism. So generally an acid would be neutralized by a base and a base would be neutralized by acids over natural conditions. So if you also want to think about those terms, then जहाँ पर भी acid होगा वहाँ पर अगर that base होगी और आपस react करेंगे salt water बनेगा, salt water बहुत normal है। But pH आपको generally like आपको याद होगा कि आपने एसिड्स के बारे में पढ़ा होगा, आपने एसिडिटी के बारे में पढ़ा होगा, आपने बेसिस के बारे में पढ़ा होगा, और आपने pH की स्केल देखी होगी 1 से 14 तक है, और जितना ज्यादा 1 के करीब जाएगा स्ट्रॉन्ग एसिड होगा, जितना ज्यादा 14 के करीब जाएगा स्ट्रॉन्ग बेस होगा। दोनों की प्रॉपर्टीज दोनों केसेस में बहुत सिमिलर है, दोनों कोरोसिव इन नेचर। और वो जो हमने एसिड रेन की बात की उससे भी आप इसको रिलेट कर सकते हैं of how that eventually then corroded the buildings, and that's sort of the impact that it has not only on buildings, man-made buildings, but also on soil. So if that same acid rain would drop onto a soil, which is generally basic in nature, जो हम देखेंगे, then it would wash all of those away with it. And if it washes those nutrients away, it would deprive an ecosystem. And some people are using phones as if I don't exist in this class, which is okay. So then you know, just look at this, and then also let's look at nitrogen. So again, like these are found naturally in the environment, even though we convert it into ammonia. But this change in state by the dissolution into water changes the pH of water. And maybe I can quickly talk about this as well. So the same change can also be monitored. And now we'll talk only a teeny tiny bit about the geographical information system that we also mentioned when we were talking about the hydrospheres. So you have all of these satellites moving up the atmosphere that are recording a lot of information for you. Oftentimes what they're recording is the electromagnetic radiations. They're just looking at a certain radiation that will be absorbed by, let's say, water, and then what it releases. Very often it's the IR or UV radiations that are that hit or are radiated back into the atmosphere. And that gives important information. For example, it could give important information about the rate at which photosynthesis is happening, the rate at which carbon is being fixed, the heat or the temperature of the water body, which we looked at. So if we remember that, then now we have a lot of these stations that give us a certain data, and I was talking about how anthropogenic activities after the Industrial Revolution has increased carbon dioxide. But there are also other stations that are now trying to monitor the pH and the carbon dioxide. And if you look at it, the salt water, the seawater pH kind of decreases when the carbon dioxide is increasing, right? And I think that could be related to. So when we talk about these, you just have to think that there's some chemistry happening behind, which is if carbon dioxide is in the atmosphere and if it diffuses into the water and if it reacts with it, its pH would decrease. And technically, some form of monitoring should be able to give you that data that there is now a decrease in pH. But if you look at it the other way around, the carbon dioxide is being diffused into water. So it is sinking into the environment. And I know this looks a little complicated, but it's super, super simple. So if you remember those three species, which is this, this, and this, how their availability will change with pH as well. So you will find this one, the more carbonate one, at a higher pH range. So when it's basic in nature, that's when you find this. So it's either this making the environment basic or a basic environment increasing the availability of this. And you can look at it either way. But the important thing for us to remember is that as the pH changes in the environment, the availability of certain form of compound and the change in type of a certain form of compound could occur, which would then impact life below water. So up until now, what we've looked, I think, mostly is the life. So mostly like what we've looked up until now is the relationship between the hydrosphere and the biosphere, if that makes sense. Yeah. I think both very acidic and very basic conditions, like I said. both have similar sort of implications. They're both corrosive in nature. So for a normal life, the pH, like the maximum pH, so neutral is something that's better, but naturally there are some issues. I think between 6.5 and 9 is ideal for life. But like I said, there is life that survives at extreme conditions as well. So without that idea, the ideal conditions generally lie between 6.5 or around neutral, so close to 7, but the maximum rate generally for widespread is in that region. I'm sorry, I cannot hear everyone very well, but I understand in line with right.
So, what I understand it, it's like really hard. They can generally outline what is the but even liquid brands so exactly like the 9 will cut off with there, if you can push it to 10 right now.
I don't know, if there last time it helped because there was a fitness freak in the class and he gave us very useful insights about nutrients and so if you look at a lot of workout drinks, they will tell you, and that's why I kept using the word electrolytes, not salts. If you look up these drinks that they generally have right after a workout, it says electrolytes and energy boosters. That's essentially the salts that are added into your body to increase the blood flow, to increase that communication that's also in the body. And then maybe it's worth looking up the pH of those particular drinks. Those pHs definitely should be higher. And like I said, towards like between 7, 8 to 9, there's a high range and probably we could go even higher, but it would depend on the function that you want for a particular thing to do. Because if you also look up then the negative impacts on these protein shakes you drink, that's also really hard. Like what happened to just eating food and making the protein source out? You're basically getting shortcut to get protein, getting shortcut to get energy. And since it's chemicals being added artificially to the body, I think they also do have complications. I haven't read that up in a great detail, but I've heard of it from different sources. So I would definitely encourage all of you, particularly those who like a drink with electrolytes, to see what the impacts of that would be on the body, to see what its exact features, because all of those definitely should be tested. And of course, we have a threshold as well. I think we can go about 9, but maybe not for a long period of time. Yes, exactly. So like, yeah, so there are different functions in the body, and then of course the deeper you go into this, the more understanding you have about life. And of course, like I said, these enzymes have enzymatic activities. इसके बगैर बहुत कुछ नहीं हो सकता, और कुछ को salt और काफी चीजें चाहिए होंगी naturally yet conditions. Distracting me, you guys. Okay, so we talked about suspended solids and dissolved solids, and it basically has to do with size. Like I said, if they're bigger size, they're suspended. Now, how do you think that has implication on life? What do you think? So if it's like a turbulent water body from Sabat, that has a lot of sediment rolled into it, versus maybe Ravi, which is not really that clean, but let's say a more calmer water body that doesn't have as much sediment load as a turbulent water body. What do you think would the impact be? And come on, some of it should be very easy to guess. So what promises life below water? Exactly. So if you have more sediments in the body, and let's say this a lake, then if the sunlight doesn't penetrate into up until a certain region, that means that the photosynthetic or the phytoplanktons wouldn't be able to grow as much, and that would then impact the entire chain. So that, that's one. It also then impacts the diffusion of gases, so even diffusion of oxygen. Although in turbulent waters there is more oxygen, but those sediments also can impact the cell and stop it from surviving. But again, I wanted to get you back to thinking about the connection that these parameters have with one another. So we talked about conductivity, and now we're talking about suspended solids and dissolved solids. And like I said, the solids are dissolved, they're not visible, they're super small in size. If there's a lot of rain, and if all the rainwater from all the watersheds gets that, combines it and forms a basin, how does that impact the suspension? So the TSS part is easy to think because, of course, the more distances and the more places it goes from, it will accumulate, dissolve more chemicals. It will take more sediments with it to a bigger water body. But then it would also then, because of the presence of salts, increase the conductivity. So what I wanted you to think about is that if there are water events, then of course the TSS will change. Of course the TDS will change because naturally water will erode a lot of the chemicals that are found there. But sometimes that would also change the conductivity. Almost always it will always change the conductivity. And this is not a standard reading, but let's say if there's more flooding, the conductivity could increase because it will now accumulate a lot of chemicals that are naturally found in the soil or artificially added as fertilizers. If there's more evaporation, again, the conductivity could increase or decrease depending on the type of water body and the type of chemical that we're talking about. Okay. And then again, if there's a runoff, so now think about all of these events and then all of those parameters that we've talked about. What could happen if there's more flooding? What could happen if there are drier periods? What would that mean for the salinity? So if you remember for the salts for the soil we said, if there's more evaporation, a lot of salt would accumulate in the soil, and that's when the salinity of the soil would increase. Okay? So, or if we want to take it away, we would flood it and wash it away, depending on the type of salt. So get rid of the salt and make the soil healthy for life. Again, up until now, is there a comment, question? Does this make sense? There's a lot of questions. Okay, I'll take yours first. Yeah. So if you look at it with energy, and I think it's interesting that you guys are making these connections. If you think in terms of energy, of course, more turbulent the water, higher the kinetic energy would be. But then if the water is calm, the potential energy would also be high. So even though a water body isn't really moving, it could still store a lot of energy. It's just potentially stored in the water. Whereas if it's moving, if it's gushing, there's a lot of energy that is related to its movement. So it's kinetic. So in terms of energy, yes, there's a whole balance there that we also need to consider. But now we're sort of zooming in into the quality and not necessarily the energy flows. We are now looking at what are some of the parameters that would change as this water body would move no matter what pace from a certain place to the other. And as this water body would stand in a certain point and interact with different gases and interact with its surroundings, no matter what the surrounding environment is like. And in that, if you look at the, for example, just a simple mountain and a water body. If there is a mountain that has more iron or more minerals, when that water moves from that mountain, it will dissolve some salts into it. So for example, if I could define conductivity for you in simple words, like I said, water generally is a more conductive to electricity. You add a little bit of salt, mix it, because now you have two electrolytes, like electrolyte added to it with a positive ion sodium and a negative ion chloride. Now when you mix it, it's highly likely that you can conduct more current. And that conductance is essentially conductive. Measuring that is conductive. Now, like I said, environment doesn't only have sodium chloride, it has a lot of other salts. And those salts would increase the conductivity. Or let's just call them electrolytes. Those electrolytes, all the positives, negatives, would contribute to the conductivity of water. And it would indicate presence of electrolytes naturally or artificially. Some of them will be important for the cycle, some of them will not be good for it. So, when we look at a eutrophic lake for dissolved oxygen, transporting all of those phosphates and nitrates that we add as fertilizers into our environment, not healthy for a water body that is consuming. On the other hand, some minerals like phosphorus or phosphate, which is needed for life, transported by a water body from a rock to a water body, very healthy for the environment because it's essential for life. So just, and I hope I've answered your question. Yes. Yeah, absolutely. So the question was, could we think that the suspension or the sediments present in the soil would impact the life and how life survives? Yeah. So there might be some fishes that need higher dissolved oxygen, but they might need clearer water bodies because they rely heavily on a certain kind of phytoplanktons, which wouldn't be able to grow with that much sediment load, or a sediment load generally is unhealthy for that particular species because it can't filter it out for itself, then automatically impact the life that's living there. But yeah, this discussion can get really complicated. I'm trying to keep it as simple as I can. So let's now think about dissolved oxygen. You should be able to make some of these connections yourself because we have talked about some of this, like indirectly I have talked about some of this. So like I said, there are naturally conditions that exist. Naturally, the dissolved oxygen of seawater is comparatively lower than in a freshwater body. Naturally, there are variations in the dissolved oxygen at a certain time in the year. And then again, it depends on the environmental condition there. The conditions that are there naturally, right? How the temperature, like I said, temperature has a relation to dissolved oxygen. So if the temperature changes, dissolved oxygen would change. But then a lot of gases presence of a pollutant would also change the presence of like the dissolved oxygen. So we talked about how, and I'll come back to this because we've already talked about this, and I'll try and bring it back again and again because I don't think some of you got the clear concept, basic concepts. So I'll come back to this again just to tell you why there's some parameters that you kind of need to know because they will pop up in a lot of environmental conversations. You kind of need to have a general idea of what someone means when they say this particular pollutant is impacting life below water. So it's impacting life below water because let's say, and as we discussed in the hydrosphere, this particular point source of pollution is being added here, and the dissolved oxygen with otherwise in the healthy range, which is 6 to 8 milligrams per liter, which kind of is shown here, that the DO of a healthy body, water body with all of this life is 8 parts per million. As soon as the point source of pollution comes in, this dissolved oxygen is going down because a lot of life, I think, is trying to degrade what has just been added in. Since the sun may not necessarily come in, it's probably impacting. And then we talked about, so look at the tolerance. We talked about tolerant species that can adapt, species that can that have a diverse range. And then there are species that just can't simply adapt. So while there might be some fishes, and look at how that would impact the food chain, right? If you remember, gar is a fish which eats all the other fishes. So when there is pollution, all the other species die, but it is more tolerant to that form of pollution. So I think what eventually could happen is, even though these fishes were able to survive the amount of pollution, if their food source is gone, if let's say this point source of pollution wasn't a point source of pollution, if the food source is gone, eventually they'll go out of the equation as well. So even just thinking that, oh, these are tolerant, that they would survive, isn't enough. So for them to survive again, their life has to kind of thrive again. And now I want to relate the concept of dissolved oxygen, because otherwise this gets complicated. So there's dissolved oxygen, which is needed by life, and also which is needed for a healthy water body. If it is devoid of oxygen, if there's no oxygen there wouldn't be any life form there. Maybe bacteria and some other species that can survive with less oxygen. But then what they'll probably do, so for example, in the water, wastewater null or channel that's just passing by lungs, there are a lot of chemicals added to it. It stinks because it probably has very little oxygen. I don't know how much because I haven't monitored it, but that smell essentially refers to the fact that there isn't enough oxygen penetrating in for microorganisms that survive with oxygen to break down the chemicals. And then it only probably allows the bacteria that can survive with complex chemicals with lesser oxygen to survive. And because there isn't that mixing, it stinks. Generally, wherever, so in the wastewater treatment bodies, if you see there's like a lot of mixing and adding oxygen to the body, because how generally the degradation happens is you allow for the bacteria that can thrive in the presence of oxygen to kind of degrade the waste components first, then the bacteria that can survive without oxygen. So there might be a lot of chemicals that would only degrade in oxic conditions, so you allow for those bacteria to degrade the chemicals, and then eventually get water close to a clean water body. So like we said, the wastewater is practically 99% fresh water and 1% bugs and chemicals. But then the impact that it would have is huge, right? So the biological oxygen demand is the oxygen that is required for life to survive. So all of this body, like a biosphere, or the life biota that died because their BOD wasn't met, right? And their BOD increased. So when there's enough dissolved oxygen, their demand would be low because there's enough dissolved oxygen. But if there is the dissolved oxygen goes down, the demand will go up because now there's not enough oxygen for them, and they're breathing, they're trying to survive, and their BOD would increase. And bear with me until I finish this. And then, as let's say there will be more mixing, dilution, some of the smaller fishes will then grow and try and survive that condition. Eventually, if there's no more pollution being added, this dissolved oxygen should try and come back up. So where it started from 8 ppm to then facing this shock, to then diluting and life coming back, and the DO coming back to 8 ppm. What we also said is that if the dissolved oxygen decreases, no matter what the source is, even if it's like a heated nuclear waste, even if it's like a dump from municipal waste or a dump from industry, the dissolved oxygen will go down and then the demand would increase. So the BOD or increasing BOD is an indication of presence of pollution and the fact that life is no longer surviving in that water. And the COD is basically another form of it, which is that all the oxygen that will now be required to degrade the chemicals that are present there. So any organic compound that is coming from here into the water body needs to be taken care of. And there might be a lot of bacteria and other species that's fungi that want to take care of it, but they also have oxygen requirements. So to degrade those chemicals, you also need enough oxygen. So they're not mutually like exclusive, but they're in a way that one doesn't guarantee the other. So if there's enough BOD, that's when the life will be able to divide or degrade that chemical, unless of course it can operate in anaerobic conditions. So they're not really two different things, but are two different things, if that makes sense. Behram, you had a question or comment? So the bacteria that we're talking about here are not the autotrophic bacteria. They are probably heterotrophic bacteria, जिनको आप अपना food खुद नहीं बनाना. They kind of have to scavenge everything that's present. And I hope I can focus on this in the lecture on microorganisms, of how there are different kinds of bacteria, and why again that diversity allows for them to survive in such diverse environments. So survival of bacteria is easy, but then the role that they play in the environment is also super important, because there are all kinds of bacteria and there are all kinds of environments they can survive, and how they adapt to different environments. In this particular case, it's definitely heterotrophic bacteria or anaerobic bacteria that do not necessarily need oxygen, light, and all the other conditions that they generally need. I think in terms of survival, both bacteria and fungi, and even a lot of life in the desert, right? That is just living there and will only thrive when there's enough rain, right? वो उनकी adaptability और उनका survival और उनका mechanism of fighting and staying strong in environment. Just like there are species that are really, really critical to how the little changes in the environment, there are species that are really robust and have different mechanisms of survival. And bacteria is one of them. I think the diversity in the range and in the kind and in how they survive. And okay, here we said कि अभी उनके पास oxygen नहीं है. If there's now a pollutant that they need to degrade, but that's an environment that some bacteria might be able to survive. But imagine that if the conditions were really worse and if there was no food at all, they would even then form spores, and this is true for both bacteria and fungi, because they would form these spores and just stay dormant, just like a virus. So virus is like non-living, so these will not necessarily be non-living, they'll be living, but they'll be dormant. And they'll just be waiting for the perfect conditions to come in. And I think that's the degree of resilience that probably the biosphere needs to show to survive some of these shocks that climate change is going to bring. But yeah, I mean, interesting point and interesting discussion that the species that have come this far are the species that are really diverse. And I think we are surviving a lot because we also are super diverse in how we navigate and how we, particularly with changes, like how we adapt to everything and how we're trying to survive by being
I have two questions. Firstly, what is COD, chemical oxygen demand?
BOD is biological oxygen demand, so the oxygen required by the life, whereas COD is the chemical oxygen demand. So the oxygen that the life would need to degrade the chemicals that are being added into.
Chemical oxygen demand is the sum of these both.
Yeah. So the oxygen that the life would need to survive, which could be minimal, right? Just enough to breathe. But now I have an additional task cyanobacteria to also degrade the chemical for you and bring the environment back. So the COD would always be higher than the BOD. It's not just the oxygen that I need to survive, but it's also the oxygen now that I need to use to break the chemicals.
And then secondly, anaerobic aspiration, often lactic acid and somewhat acid is produced. So won't anaerobic aspiration cause the water body to become acidic?
So weak acids, like even in the case of carbonic acid, I think weak acids are okay because we said we can survive between 6.5 and 9. So as long as any byproduct isn't increasing the pH to 1 or 2 or 3 or 4 or 5, we're okay. So as long as it's a weak acid, they're naturally
That does
like a
not
lot.
disrupt natural
Yeah,
balance much.
yeah. And if it does, then of course life doesn't really thrive, right? Okay, does anyone remember any of these from the MSDS that you saw? Was there any sign that you remember from the MSDS sheets? So these are the signs that are generally used in the lab, and you may not, a lot of them may not apply to you, but your MSDS should have some of these signs like carcinogenic, or poisonous, or particularly I think this one, which generally comes in ways. So this is more to do with environment. I just put some of these there because I think these are the signs that you should be careful about. It will tell you exactly what hazards, these are like hazard signs. So just like I was saying, there's not enough information given to the people who have those information, should have those informations. These are some representative signs of what something could mean. So for example, for battery, for a chip, you know, there are a lot of these signs that you should be aware of, but I thought that it's as a student in this field, it would be nice for you to, for example, when you're looking at the MSDS, forget the MSDS and just look for these signs and say, I know this is carcinogenic because I know this sign. So sometimes like these sign postings really help inform people as well. So you don't necessarily need to remember this, but you definitely need to know this. Which brings me to what we'll be talking about on this while, the DDT, and so many more chemicals that are considered or put into a category called persistent organic pollutants or POPs. So just like SOx and NOx and all of these terms that you hear in the environmental sciences are bad for the environment, POPs really, really are bad for the environment. And there's so many case studies that are just lying there. You must have heard about, of course, we've talked about DDT, but you also must have heard about terms like dioxins. And I might have used it without knowing, but you know, with plastic pollution, we say they add a lot of dioxins. They release dioxins when you burn them. So essentially, it's the box that I'm referring to when I talk about dioxins. And again, like dibenzofurans or dioxins, they're all byproducts that we didn't really think too much about. So we were creating plastic and we didn't really think about what else would bring to our environment. When we were creating pesticides, we didn't really think about some of these byproducts that would eventually be released into the environment. And it's also when these chemicals like dieldrin or some of these pesticides that eventually showed in the environments that they were thrown in. You know, when you found deformed eggs and deformed birds and deformed children and children without limbs, and you know, suddenly it was a wake-up call to people on, you know, exactly what we're doing wrong. And then it was related to the food, or it was related to the food that the mother ate, and then it was related to, you know, the source, and eventually the source went down to some of these chemicals which were released into the atmosphere or in the all the spheres of the environment, found their way to our body, found their way to the body of all the other life forms, and caused nuisance that we weren't ready for. So then suddenly, like, we banned all of these things. So a lot of these POPs are now banned, even if some of the pesticides still are POPs there. They can stay in the environment for thousands of years. So they're called persistent because they do not degrade easily. They're called persistent because they're just there, just like plastic. They're there for thousands of years. We throw it, but we do not know how many generations later it will still be there as original POPs, destroying life forms. So And then I think I just want to mention this. We'll talk about some of the multilateral environmental activities later. That there were then laws that were passed, there were bans that were imposed, and we'll get to the UN and UNFCCCs and all the laws that were created. But just an indication for you, and I think I didn't want to put too many chemicals or too many indicators in the lecture, but I also thought that some of them have really been like the biggest alarm for the planet, and POX is one of them. And still is. It was one of them, and it still is. So which is why I've kept it like last year in the lecture, because I'll also be mentioning this in some of the other things. How much time do we have? Maybe we can quickly touch upon heavy metals, and then take some questions if there's time. So how many of you heard of heavy metals? Just heard of it. Yeah, a lot of us have heard of heavy metals, right? We talk about the presence of heavy metals such as arsenic in the groundwater of the earth. Why is it so bad for the earth? First of all, we need to understand why they're called heavy. They're called heavy because they are dense. They have higher density. So if their density is above 6 grams per centimeter cube, and I've put some of these indicators for you to see that, for example, their relative atomic masses could vary. Some of their other characteristics could vary. But what makes them heavy is their density. So just think of metals in the periodic table that are heavier than the rest. And because of that particular characteristic, they cause different things in the environment, which is why we need to be cautious about their presence in the environment. And it is natural. I'll come back to some of the questions when I'm done with this section. So bear with me for a minute. So like I said, why should we worry? And we're trying to talk about, so in the previous section, we got to look more at the interaction of hydrosphere with biosphere. So it's essentially life in water that we're looking at. We're looking at water quality parameters, whether they come from the atmosphere or the lithosphere into the water body that is then interacting with the life. Right now, we're thinking of us and how some of these heavy metals impact us, and which particular organ do they hit, and what is the toxicity that they cause. So oftentimes the sweeping statement that we give if we do not know too much about heavy metals is that they are toxic for life. But what kind of toxicity do they cause? And that toxicity could vary depending on the heavy metal, and some of them are toxic to many organs, not just one. So let's say if we take the case of arsenic, which we say is in abundance in the groundwater of the earth, it's heavily impact, is related to both natural and artificial or man-made sources. What does it cause? Hepatotoxicity. So it damages our liver, and liver we know is important in detoxifying a lot of things in our body. And similarly, like all the other, so for example, this is interesting, right? Zinc is essential for your body, but excessive zinc also causes hemotoxicity. So it does cause toxicity in the blood. So sometimes what's essential for you in a certain quantity is toxic for you when it's given to you in bigger quantities. So again, that how the change in your environment changes your being and your body and the kind of toxicity that they cause. So that I thought would be an interesting information. I will not be talking about all the heavy metals, but I've added some information on one or two heavy metals here, which is lead. So generally, like you hear about lead all the time. You probably hear about lead-free gasoline, or this fossil fuel is now lead-free. So you remove the lead because we know that lead is not good for us and it's not good for all the other life forms, and it's a pollutant in the spheres of the environment. Like you read here, it's toxic for flora and fauna, so not just plants, but also not just animals, but also plants. So how we are, but then if you look at it, it's still found in abundance in certain products that we create. And why is that? Because I think we need some of these, and some of these are being replaced. Maybe the last concept that I covered, and take a break here. How does this heavy metal impact the lithosphere? So soils generally, as we studied in the lithosphere, are alkaline in nature. You have calcium, magnesium, etc. in the soil. They're generally alkaline in nature, which is why when the acid rains, it impacts, it washes these nutrients away. So that's naturally how they are. But how do these heavy metals impact some of the soil components? So naturally, like soil has, and again, this is just for your information of how complicated these structures are. So generally, you have these complexes that are found in the soil. So humic acid is really important because it's related to the organic content and the nutrients that plants get. But if these heavy metals combine with those, they can, instead of keeping them bioavailable, precipitate them. So take them out of the sphere, take them out of the reach for the plant and make them unavailable for the plant. So that's how they impact the lithosphere, and then eventually the life that is found below it. And I've summarized kind of the same in here of how when it is absorbed into the soil, it will take that nutrient away by precipitating it, by taking it out of the solution. The opposite is also true. Sometimes they dissolve something that's not healthy for the plant into the water. So they could form complexes where arsenic or other heavy metals are now available for a plant. So the bioavailability could be impacted both ways. One time, an important nutrient was taken out of the reach for a plant. The other time, a toxic metal was added or made bioavailable. And that has a relation again to pH as well. So for example, I said naturally the soil is alkaline. If it becomes acidic, some of these heavy metals would become bioavailable for the plant. And if the plant takes it up and we eat it and we keep eating it, then it would build up in our food chain and bring us back to what we were discussing, which is biomechanics. So imagine if there's an effluent from a certain industry of Faisalabad that has a lot of lead that is going into the field, and I end up eating that vegetable. Even though it's in smaller quantities, I end up getting vegetables from the same farms, and in the longer run, I have the toxicity that is caused by that heavy metal. So I think we can stop there because I know I had quite a few things to discuss. So let's just stop it there. And